Right, so we're going to move on to some other functions that you have to be able to differentiate. So far you've purely dealt with polynomials, which hopefully you remember is a series of powers of x. So for example, x cubed add 3x to the 2/3, etc. But now we're going to introduce a few other functions. This video is going to deal with e and log, or the natural log. Other functions you might need to differentiate would be sine, cos, tan, some other trig functions you're yet to learn about. All of those will be introduced in the next few videos. So the basics are that if you have y equals e to the x, it just differentiates to e to the x. Now that is because of what the exponential function is actually defined as. So the exponential function was created in a way so that the gradient at any point is always the same as its y-coordinate. So if the y-coordinate equals e to the x, then the gradient equals e to the x as well. If you have a more complicated function to do involving e, so e to anything else, it's a bit trickier, but we'll come to that in a second. And then the opposite of e, the inverse of e, is log of x, the natural log of x. So if you have y equals the natural log of x and you differentiate it, you get 1 over x. Again, more complicated if you have a more awkward function involving logs. So generally, e to any function, when you differentiate it, you still get e to that function, but you have to multiply by the differential of that function. It's actually a version of the chain rule, but I'm not going to go quite into that right now. But if it's just the differential of the function times by the original e to the power of that function. And for log, if you have the natural log of x, if you differentiate it, it differentiates to the function on the bottom and the differential of the function on the top. So it always forms a fraction. Differential on top, the function on the bottom. Which if you look back at the natural log of x, if you differentiate it, you have 1, which is why 1's on top, and the function itself is x on the bottom. So we'll start with a few examples. So if I have y equals 3e to the 2x, if that was just 3e to the x, then it would differentiate to 3e to the x, but it's not. So when we differentiate it, we have to multiply by the differential of this function. So hopefully you can see that there, differential of that function. So you have 2 lots of 3e to the 2x, or 6e to the 2x. And the most basic natural log, just differentiated to 1 over x. Now, funnily enough, this will actually do the same, and I'll explain why in a second. But if we just follow the general rule that I've written above it, if you differentiate 2x, you get 2. And if you put the function underneath, it's 2x. And that cancels down to 1 over x. Now you might wonder, well, why does log of x differentiate to 1 over x and log of 2x also differentiate to 1 over x? Now, if you hopefully have looked through your log laws that we did before, then you could say, actually, well, the natural log of x is equal to log of 2 add log of x. And if we differentiate this, 1 over x is the differential of log x, and log 2 is actually just a number, and for all intents and purposes, a number disappears when you differentiate it. So this just differentiates to 1 over x using this method as well. But, so you can remember that if you have log of any number of x, just any number of x, if you add something else afterwards, it's not the case. But if it's just log of something x, it will differentiate to 1 over x. Right, a few more examples. So y equals e to the x squared plus 5x. So, quite straightforward. Just focus that again, don't know why that's gone out. Sorry about that. So if you differentiate the function, you would have 2x add 5, and you multiply it by the original e to the power of the function. So just to show that next side by side, e to the function differential is the differential of the function, which that goes to 2x add 5, times by the original question, which was e to the x squared add 5x. And for log of x, if you differentiate it, then you put the original function on the bottom, and on the top, you do the differential of this. So x squared differentiates to 2x, 4x differentiates to 4, and then we just have a plus 4, which differentiates to 0. Now this one, I've not said I have to simplify it, but funnily enough, this one does simplify. So if you look, you could actually factorise the top so that you have 2 lots of x plus 2, and the bottom is actually x plus 2x plus 2, because it's two things that multiply to 4 and add to 4 are 2 and 2. So that one actually cancels down quite nicely to that. I can show you another way involving log laws where you could get from that to that a little bit quicker, but I'll leave that for you to have a think about. And if anyone wants to ask me about it, just send me a message. So, other things you could have to do is you could have to use the product rule that we did the other day, and you could also have to use the quotient rule. So I've done one example of each. So if you remember, dy by dx is u dash v plus uv dash if you have essentially 7x is your u and e to the 2x is your v, because we have two things multiplied there. So if we differentiate 7x, that would give you 7. And if we differentiate e to the 2x, you're left with 2e to the 2x. Plug that into here. dy by dx would be u dash times v, so 7e to the 2x, plus uv dash, so 7x times by this, 2e to the 2x. So altogether, you would have 7e to the 2x add 14x e to the 2x. So say product rules still apply as they did before. And the quotient rule will also apply. So if you remember, the quotient rule is u dash v minus uv dash over v squared. And that's u and v again. So let's work out what uv, u dash and v dash are. So u is log of x squared and v is 2x. Remember, it has to be that when you're talking about the quotient rule, that u is the numerator and v is the denominator. In the product rule, it didn't matter which way around it was, but it does on this. So u dash will be, well, if we differentiate this, what you have to do is you put the original thing on the bottom, so x squared on the bottom of the fraction. Differential of it is 2x, so that goes on top. And we could cancel that down to 2 over x. V, well, 2x just differentiates to 2. So let's pop this into the equation. So dy by dx would be u dash, which is 2 over x, times by v, which is 2x, minus uv dash, so it's these two times together, 2 log x squared, all over v squared, so over 2x all squared. I'm going to simplify that a little bit. So 2 over x times 2x, well, divide by x and multiply by x cancel, so you're just left with 2 times 2, which is 4, minus 2 log x squared all over 4x squared. Now that would be an acceptable answer, but I've mentioned log laws a few times today, so I'll bring them back in again. If you remember, if you have log of x squared, and the squared has to be inside the brackets, it can't be log x all squared. But if you have log of x squared, you can bring this power down to the front. So that would mean that log x squared is the same as 2 log x. 2 times 2 is 4, so you have 4 minus 4 log x over 4x squared. And if you divide the top and the bottom by 4, 1 minus log x over x squared. Okay, so that's hopefully a good summary of the things you can do with e and log x involving the product rule and the quotient rule. The next video, I'm going to start working through differentiating sine and cos, and then we'll go on to tan and other trig functions in a future video.